So I solved this problem in another video using phasors. So this time I'm going to use complex number analysis. And again, we have the same specs. If you've seen the other video, resistance 15 ohms, my inductance 45 millihenries, my capacitance 200 microfarads. We have a power supply with 120 volts, 60 hertz, and I'm going to establish that as my base or my reference point, reference angle. And so from the RMS value, we get a maximum value of 169.706 volts. From the frequency of 60 hertz, we get an angular frequency of 376.991 radians per second. And so we can quickly establish what the instantaneous voltage of the power supply is. And this notation here, this is basically the magnitude and the phase shift. There's an understanding that there's a much larger equation there that could be written as VPS is equal to 169.706 volts cosine of 376, man, I'm going to run out of room there, 0.991 radians per second times time plus my phase of 0. It also could be understood that this is equal to 169.706 volts times e to the I omega t plus 0. This is one of the bases of this, that for any of these functions here, I can write it as some amplitude times e to the I omega t plus phi, which would then be a e to the I omega t, e to the I phi. And so this is common to all of the functions that we are creating here, and these are the ones that are different. But this also allows us to, when we're dividing quantities in polar form, we can just subtract, or if we're multiplying, we can just add, because e to the, we'll just say 2i over e to the 0.5i, well, you would just subtract that number right there. And so that'd be e to the 1.5i. And e to the 2i times e to the 0.5i would be e to the 2.5i, or I 2.5. Now, one other thing is that I'm using I here to represent the imaginary number, square root of -1, but since I actually use I, this lowercase I, for current, it is common often to use J for the square root of -1, and so that is what I'll be using from now on. From this information here, since I know what the angular frequency is, I can figure out what the inductive reactance and the capacitive reactance are. And then there's these other bits down here, which a number of sources are calling impedance. So I usually think of impedance as being for an entire circuit, sort of the effective resistance of an entire circuit. Some definitions don't go to that narrow definition. Some just go to the effective resistance of a particular component. And so for the components, I decided to put an extra line through my Z's here. And so, whether I'm 100% or not, don't know, but I will call this Z sub L and Z sub C, just to differentiate it from the impedance, which is the term I'm using for the entire circuit. But in essence, it's the effective resistance of a particular component. So for the inductor, it's just J times X sub L. So this is J omega L, or Jx sub L. For a capacitor, it's 1 over J omega C, which is X sub C over J. And remember, if J is square root of -1, if I have 1 over J, if I multiply by J over J, I get -1 on the bottom, I get J on top, so it's negative J. And so this is the same as negative Jx sub C, and so that's why you have the negative Jx sub C and then Jx sub L. In polar form, because if you imagine that my axes here, I have a real axis and an imaginary axis, and so this is in the imaginary, it's all imaginary. So that would be up there, that's a 90-degree angle, and then here negative J puts me down here, so that is a negative 90 degrees, or in radians, pi over 2. So now in this form right here, we now basically treat it like we're adding equivalent resistance, because I know that my impedance for my resistor here is R, for my inductor is JXL. For my capacitor, it's negative JXC. So for this middle part here, sort of ZRL, it's just the sum of those two impedances or effective resistances, which is just 15 plus J times 16.965, and that is in ohms. In polar form, it is, well, we'll do a little Pythagorean theorem. We'll get the magnitude here, and the angle is, we have some angle here, and the arctan of the opposite over the adjacent is equal to the angle, and so we get that. And so that is in degrees, and this is polar form with that in radians. The current flowing through here should be the V sub RL over ZRL. Now, the voltage across here should be the same as the voltage across there, same as the voltage across there, because it's path independent for my potential differences. And so I have a magnitude of 169.706 over that. Doing the math from polar form, first I put this in polar form, and so my front piece is just that simple division problem, and then I'm dividing, well, with polar form, it's that minus that, so it's negative 0.8679 with a magnitude of 7.494 amps. Z sub C, negative JX sub C, and so as seen on the other page. And so the current flowing down this branch is just V sub C over Z sub C. And going through a similar process, we end up with our front piece right here, which is where we divide that. We end up with 12.795 amps. And my angle, well, it's 0 minus negative pi over 2, and that's just pi over 2. For the power supply, I from the power supply coming in, it now goes through the two branches right here. So this should just be the sum of those two. So let me add those two. So that's my IRL and my IC, and I add them together. Now when adding complex numbers, polar form is not particularly convenient, so we put them each into rectangular form. And this is the magnitude times the cosine of the angle will get you this, magnitude times the sine of the angle will get you that, and similar over here. Since this is pi over 2, that's acting straight up, there is no real component, it's all imaginary. And so we end up just adding like parts, and we end up with a total real part, a total imaginary part, and then an angle. If you've seen the other video, you know how difficult finding that angle was. So the total impedance is VPS over IPS, and so we just do a division of the magnitude of VPS over the current that we just found, and so we have our front part right here, and that should be ohms, and then the angle just subtract. So now we can find the voltage across each of them, and that's just voltage across the resistor is the current across it times the resistance. So I take my current, multiply times my resistance, and I get this. For V sub L, I take my current that I just found times my Z sub L, and again just adding those two to get this, and then multiplying the magnitudes to get that. And now we're going to check, because the sum of these two should be the same as for the power supply. So the potential between these two should be the same potential going that way or this way, and so I should end up with what I end up with, or at least close enough. But when I'm adding these two voltages, voltage across here plus voltage across there, I put them back into rectangular form again. Magnitude times the cosine, magnitude times the sine, magnitude times the cosine, magnitude times the sine. My two imaginary parts cancel out, and I'm left with pretty darn close to what I had before. I think it was 706 instead of 7029, 706. And so now I have my equations right here. And that is just a whole lot easier than what we had just done in the other video, or what you will see in the other video. And so now I put in the full form where I've got the actual omega values in and the cosine. Alternatively, we could have found the total impedance by 1 over ZC plus 1 over ZRL. Now, it depends on what point you want to put in numbers, but working out in terms of letters, I've got 1 over Z sub C, 1 over Z sub RL, and then I go ahead and get a common denominator, add them, and so the total impedance is just the reciprocal of that. And I think if you watch the class video, I actually plug in numbers fairly quickly instead of going through all of this. But you end up with this as the formula with a real part in the imaginary part. And then once you plug the numbers in, you end up with a total impedance of 19.440 ohms with that angle. And if we flip back, that is what we had before. We should probably also check. So let's do a quick check. So let's pick a time of 1/720 and make that seconds. And I got 7.106 down here, negative 6.398, 0.709. And so we can do a quick check here. These are all in amperes, that the sum of the current going across R and L plus the sum of the current going across the capacitor should add up to this. So if I add these two together, I end up with 0.7085. It would round off to 708 if I took it that far. Now on the voltages, I should get the sum of these two should equal. I didn't actually write it down here, but this is also equal to V sub C, lowercase v. So let's check that out. 106.59, 40.38, and I add them together, and I get 146.97, and miswrote a number there. And this is 146.97. Those are in volts, and it matches. Excellent.